Good morning. We're now looking at Chapter 7, Equilibrium. Equilibrium relies on a strong understanding of theory to have the math portion make sense a little bit later on in the unit. We're spending today looking at an understanding of what equilibrium is from a theoretical perspective and a graphing perspective. Chapter 6 finished with an inadvertent example of equilibrium. The problem here is that there wasn't a balance in the park bench. When I got up, my weight left. There was an uneven distribution of weight, and the whole teeter-totter shifted in one direction. The teeter-totter was at equilibrium, everything shifted, and equilibrium was reestablished in a different place. Everyone on the other bench was now sitting on the ground at the end. So we see equilibrium as being a balancing of forces. What is equilibrium? Again, it's the balancing of two opposite processes. You and your parents fighting over who gets to control what inside the house is an example of equilibrium, because after the fighting, some kind of balance is struck. People in a tug of war fighting over the rope, another example of equilibrium. When the tug of war is at a standstill, we see equilibrium. At some point, one team loses, the other team falls over, capitulates, and then we see that uneven distribution of force. Whether you are riding a unicycle, whether you're balancing a chair on the edge of a tall building, these are all cases where someone or something is in a state of equilibrium. There are also chemical examples we see in real life that show equilibrium. The most common is a water bottle. If you drink half of the contents of a water bottle and leave it sitting closed, you'll notice over time condensation appears in the top of the water bottle and most of the water remains at the bottom. This is an example of equilibrium because water is evaporating and becoming a gas, then it's condensing and becoming water liquid again. Some of it will go back into solution, other ones remain on the sides of the container. So does this mean the amount of water vapor in the container and the amount of water as a liquid are the same? Well, we can apply this to equilibrium as a whole. At equilibrium, the reactants and the products have the same quantity. Is that true or false? It's false. At equilibrium, we may not have the same amounts or quantities, but what we do have is an equal rate of transfer. In this slide, we see water becoming gas, gas becoming water. That rate is the same, although the quantities of the two may not be the same. The best analogy here is a classroom where someone goes to the washroom. One person leaves at a time. So potentially you could always have one person out of the room. The rate of people leaving and returning is the same, but the majority of people are remaining in the classroom. A simple example of equilibrium in chemistry would also include the ionization of acetic acid in water. The proton leaves the acetic acid as it is solvated by the water, making hydronium, H3O+, and the acetate ion. This process, up to this point, has been indicated as something that moves forward, and that's it. In reality, this process moves in both directions and is existing as an equilibrium. The double arrow in the middle tells us that the reaction proceeds in both the forward and the reverse direction. In fact, this even means we could write the whole reaction switched around and it would still be correct. Products and reactants in equilibrium are often a matter of perspective. Other types of equilibrium that you'll read about in the textbook include phase equilibrium between ice and water, and phase equilibrium between water and vapor, as we saw in the bottle. Solubility equilibrium also exists in something like carbon dioxide dissolved in a soft drink like Coca-Cola. Which of the following is an example of equilibrium? A can of open Coke, a closed but empty bottle, a helium balloon 20 minutes after release, or all of the above are examples of equilibrium. If you said the helium balloon, you are correct. An open can of Coke is not considered to be at equilibrium because the can is open. The argument that it is at equilibrium with the entire atmosphere like the helium balloon doesn't hold any weight because the equilibrium we're talking about with respect to a soft drink is the solubility equilibrium. We need a closed system for an equilibrium. In part B, we have the closed system, but we don't have any chemicals that make up the system. So we just essentially have a closed container. There's no equilibrium there. If you wanted to argue that it was sitting on a desk and therefore it was at equilibrium with the desk, you could. Again, you're sort of missing the point though about having a system that we can discuss in some respects. Finally, C is the best answer. Let's take a look at this now from a graphing perspective. In chapter 6, we learned that the rate of the forward reaction decreases with time because it becomes harder for the reactants to find each other. This also means that the concentration of products starts building up. As the concentration of products starts building up, it's possible for the reverse reaction to occur. The reverse reaction requires products to be present before it can occur. So as the reaction time progresses, the concentration of products builds up. That means it's easier for products to find each other and therefore react in the reverse direction. So as time goes on, the rate of the reverse reaction is going to increase because it gets easier and easier for products to find each other and become or revert to reactants. Over time, the rate of the forward reaction and the rate of the reverse reaction meet, and this is called equilibrium. So we know a couple things. We know that rate forward equals rate reverse is the definition of equilibrium. And we also know that this grade 11 type of general reaction occurs in the reverse direction. At this point, I'm going to take a break from the PowerPoint. You can definitely take a look at that on your own time to finish that up. I'm going to switch over to a whiteboard so we can see exactly what's happening. When you access the PowerPoint and look through it later today, take a look at the simulation below, as well as some of the other comments that have been made in the PowerPoint that will help you understand what we're talking about. So we know that A and B react to give us C plus D. We also know that rate forward equals the rate reverse. Now we can take the rate laws from chapter 6 and apply them here. So the rate law of the forward reaction, I'll use red for that one, is going to be the concentration of A to the A and B to the B. So rate forward equals the K of the forward reaction times the concentration of A to the power of A and B to the power of B. Now something important to point out here. If you have not read chapter or section 6.4, you'll wonder where these small letters came from. In the rate limiting step, A and B, lowercase, as the exponents are equivalent to the m and n values because the coefficients are the m and n values in the rate limiting step. In equilibrium, every example we have, we're dealing with that rate limiting step. Let's look at the reverse reaction now. In the reverse reaction, we would have the C and D coefficient here. You can put them there. We're going to show them as the exponents right here. C to the C, D to the D, just to remind us what their significance is in the rate law. So the K of the reverse reaction is going to be C to the power of C and D to the power of D. Now this means now that we're able to rearrange our equation in the next line, and we're able to equate products and reactants with respect to a KQ value. Our KQ value is going to put KR on one side, leaving the concentration of C's and D's over concentration of our reactants. And of course on the, let me get rid of that. Of course on this side now we're left with K of the Ford reaction, and this side we have A to the A and B to the B. This means that our KQ expression is essentially the ratio of our K values, Kf to Kr. Or we can say this expression here equals KEQ. So KEQ essentially is the concentration of products compared to reactants using the coefficients and exponents that are there. Using information we already know now about KQ and what KQ is, let's try an actual question. You're going to need a piece of paper for this as we solve it together. Smog is made from the second order reaction of nitrogen dioxide to make dinitrogen tetroxide. The initial concentration of nitrogen dioxide is 0.1 moles in a 1 liter container, but only 0.016 moles per liter at equilibrium. Determine the equilibrium constant using a version of the previous equation. Yes, to find out what the KQ value is. The KQ value, you might remember, is products over reactants. So off to the side here, I'm going to write KQ equals products over reactants. Just remind ourselves what it is. Of course, the actual equation is the concentration of C to the power of C, D to the power of D, over A to the A and B to the B, which we previously addressed. Now, if we want to solve what this is, we need to have numerical values for the concentrations at equilibrium. That means that the value that we have right here is going to relate to the equilibrium concentrations existing over here. This table allows us to start with what we have and figure out what our final concentrations are. So let's do that. The question says that we have 0.1 moles per liter of our reactant nitrogen dioxide, and we can assume we don't have any product because we're not told about it. The change is going to be a minus 2x magnitude, and that's because every 2 moles of this that are used up, 1 mole of product is produced. So we're going to lose 2 moles here to gain 1 mole over there. Hence the equilibrium concentration is going to be 0.1 minus 2x. Equilibrium concentration here will be 0 plus x. We'll just leave that as being x. Now right away we can see if we substitute in our equilibrium concentrations and we have an unknown KEQ, we have one equation with 2 unknowns. Fortunately, looking back at the question, what we see is that we're told at equilibrium the concentration is 0.16 moles per liter. Let's put in that value now. So 0.1 minus 2x equals 0.016. A little bit outside of the box. Taking a minute, we can solve for x. And we solve for x, we get 0.042. So x is 0.042. If x is 0.042, we can now substitute in our equation values here. So we want products over reactants. Well, the product is nitrogen dioxide. Sorry, dinitrogen tetroxide. Its value is x. So I'm going to substitute in 0.042 as the product concentration. There's no exponent in the front here. There's no reason for an exponent up here. The reactant concentration, on the other hand, is going to be 0.042 as part of the minus 2x as part of 0.01. So in fact, this part here the reactant concentration is given in the question. It's 0.016. Now, The reactant concentration is given in the question. The reactant concentration is 0.016 in brackets because it's going to be squared. It's squared because the reaction is second order with respect to nitrogen dioxide, and that has to be reflected here. Remember, the origin of this squared is the rate law we previously saw. Once we put those values in, we can solve for x, and we get a value of 160, or 1.6 times 10 to the 2. The scientific notation would be important because it tells us that the 0 is not a significant figure. In this course, the textbook uses significant figures. I'm not too worried about that, but if there's an answer where one has significant figures, one doesn't, the one with significant figures would be correct. This ice table is essentially the basis of chapter 7 and 8 because all that we want to do is figure out what's happening at equilibrium because that tells us how to set up our reactions. So you'll see this in section 7.1, 7.2, 7.3, and onward. Right now, work your way through chapter 7, see how well you do with that. If you get stuck, let me know. It's a ton of stuff in today's lesson, and I wish you all the best. Any questions, email, and we'll have a tutorial session on Thursday as well.